can you show us your computed density of states for 3 different cases? So, right? So when we compute the, by the way, so let me ask like this: how many K points do you have in your calculation for in the self-consistent field calculation for your lithium structure? Right, so we have supercells. That were like 2 by 2 by 2 and 3 by 3 by 3. And then we have the unit cell too, but that is 1 by 1 by 1. Right, so how many K points do we, or did you use?
And for the 3, 3, 3, I noticed that the formula is 2 little, so I changed to 2.
Okay, 2, 2, 2. So why don't we revisit this one then and say 3, 3, 3. Okay, and this one 6, 6, 6. At least, right? So you want to try again? So, right. So you optimized lithium 222 looks something like this here, right? So, did you manage to check your structure? So when you have something, you can use it. So first I show you the output of my structure relaxation for the lithium 222. That's a rather long file, right? But it starts, I run that calculation 30th of April, 1030, 16 processors, very good. And then there's a lot of information given, but what I'm actually only interested in is did the calculation finish to compute the optimized structure. So what I'm looking for is basically end of final geometry. So I have here a couple of K points. I can go to the end basically, and from there I go up a bit. Result of the K point, final calculation. Here, final coordinates. So what I'm looking for is the line end final coordinates. And then I scroll up a bit, right? I see the atomic positions, I see the cell parameters. But what I'm more interested in is actually if my calculation converged, and here is something written like end of BFGS, geometry optimization. And when that is said to be converged in a number of cycles, then I'm happy. So I have a 9 BFGS steps. Then I check my pressure, P in kilobar. That is 0.5 kilobar, that is okay. Often values between 10 kilobar are acceptable. I can go up a bit more and look at the forces acting on atoms. The unit, right, is not given in Newton, it's given in energy over distance. Right, so Newton meter divided by meter is Newton. Right, so energy divided by length is force. Okay, and then I see for the atom 1, it tells me what type it is, and gives me the force for, in 3 components, right? X component, Y component, Z component. And for the first atom, that is all 0, very good. And then the largest value I can here identify are like 1, 2, 3, 4, 5 zeros, and then a value. So that value is very low. The total forces, so when they sum it up and average it, is also very low, and so that is good. Low forces, always good, and often it's said that you should aim for a force convergence of 0.02 electron volts over Angstrom. How do you convert electron volt Armstrong in Rydberg per Bohr? Atomic unit here is Bohr, 1 Bohr. Right, you figure that out. 1 Rydberg is 13 point, actually I know 27.211 divided by 2 Rydberg, and 1 Armstrong Bohr is roughly 0.59 Armstrong, like that. Right, so estimating there's a factor of 20 here, so we divide that by 20, we get 1 more 0, so we should have at least 0, 0, 1 here, and that is what we have in all components. So that is looking good. So our structure optimization successfully completed. Then I go to back to after this check, if the structure optimization really succeeded, I try to find where is it? My final coordinates. And again, I copy, as we have done previously, I copy the cell parameters and the atomic positions. Copy. And I store that in a temporary file. Let's see. It's my right. So that I have it when I need it. Right, and that's all what I need from that. Then I have created already a new directory called density of state. I copied my old input file in the new one, so I have the old calculation used the volume of the unit cell relaxation, meaning the atomic position and the shape of the unit cell optimized. So the basis and the lattice optimized. To compute the density of state, I of course change this to SCF. And I delete. I have 16 atoms, so I press D and then 16, enter. I deleted 17 lines. I delete the next few, and then I paste in those. Okay, good. I paste in my structure. Okay. So copy paste today works very nicely. For my 222 unit cell, I use 999 K points. I have a cubic unit cell. That is not the primitive unit cell, right? It's the conventional standard. The number of bands are 60. I will check in a moment if that is good or not. Right, I go back and I open the output file of the structure optimization, in which I will check for the number of electrons. So I press Ctrl F, electrons, and I look for number of electrons. I have 48 electrons in that calculation. I have 16 atoms, meaning for each atom I have 3 electrons. Okay, it's lithium, so I have a full description of my electrons in that calculation. My number of Kohn-Charm states that is the number of bands is 60. 60 is far more than 48 divided by 2, because 2 electrons can share one state, right? Spin up, spin down. So I'm good to go. So I submit now this calculation to my queue. I can call it lithium SCF out. I check my queue. It's running. But you have done that before, right? This small repetition is just to see if you have done things differently or not. So far so good, right? You optimized your structure, volume relaxation plus atomic position relaxation. Then you look if your structure looks okay. You open the structure, you visualize the structure, you turn it around. If nothing exploded, you close X-Stem, you open the text editor, you check the output file, then you copy the final coordinates of your structure optimization, you create a new directory for the DOS calculation, you can copy your old input to the new input, paste in the optimized structure and change the calculation type from an optimization to a self-consistent field calculation. Okay, that is the preparation, and this preparation is very important for all basically production calculations of density of states, band structure, and other properties where you want to have high accuracy, right? Okay. So for example, so sometimes when you use other codes, could also happen with this one, when you have a structure optimization and then you use the results of the structure optimization to create a density of states. Sometimes for each of the ionic steps, you can save the potential and the wave function. If you then want to use intermediate results that are stored during the structure optimization to compute density of states or band structures, how do you ensure that the program you're using, that you didn't program yourself, knows which of the structures to take? Maybe it uses the first wave function, right? Maybe it uses the last wave function. As long as you're not 100% sure, you should not proceed. Therefore, we have these little steps, right? Structure optimization, copy, paste the optimized structure, and start the process of computing the electronic properties. Right? That is to have a clean process of getting information of a material. Okay, anyhow. So my SCF calculation already finished. It was pretty fast. It tells me here took a minute, 40 seconds. If you are interested to figure out what happened during your calculation, Quantum Expressor gives you a nice breakdown on how much time it spends in which part. Then you could figure out what part is doing what, and so slowly understand in more detail this little black box that we're using. Okay. So let's check again a bit. So for the SCF calculation, it's important that we get a converged electronic structure. So this result looks pretty much converged here. Then we have a couple of bands printed. So let's take one for example. Here we have the K-point in form of reciprocal lattices. That is 1/3, 1/3, and 4/9. the bands are given in EV, starting from the lowest to the highest. And to see which one is then occupied, we would need to find the value of the Fermi energy. And let's open the output. Fermi energy is roughly 1 eV. And then we take now this K point here. Okay, the last K point, no problem. It's roughly this value, and to find for that particular K point, the highest point of the valence band and the lowest point of the conduction band, we look at the values, we find the one surrounding 1 eV, right? And that would be these two. And all the others would be part of the, all the ones that are above these two values are the conduction band, and all the ones that are below are the valence band. Okay. So you managed to do that now with your calculation too, where you increased a little bit your K points, right? Did you manage to compute the density of state already? Good. So then I will look for my DOS input. This is here. So I went to the Google Drive and copy pasted the example input for the DOS calculation of benzene. There are a couple of things that we would change, because there's quite a difference to compute the density of state for an isolated system like a molecule compared to the one of a solid. Okay. let's do it one by one. So the first line here is the prefix, and the prefix needs to be adapted to give us the same prefix as in our SCF calculation. My prefix here is Le for lithium. So put lithium here. The output directory is TMP for 10. I have here the TMP directory that was created during the quantum espresso run. And if you check what's inside the TMP directory, you see there's another directory called lithium.safe and lithium.xml. XML are some information that were created during the calculation. And in the lithium safe directory, there are now wave function files, one for each non-reducible k-point. There is the potential we used, or I used, right? So Quantum Espresso is actually copy-pasting the potential file, so you can check which potential was used. There's another XML file, and that is all for now. Okay. So, and then I can try to run the DOS calculation, run DOS, and it's actually working already, okay? That is good. We can take a look at the DOS. So I open GNU plot, and then I type plot, the name of the DOS file, and then I think I need to say use column 1 and 2, and plot the information with lines. Now I need to check on which screen right. So what do I have here? So something didn't work with lines. Right, because I'm a bit stupid. I forgot the using. Okay. Now, so what do I have here? That's now my density of state, right? Do you like my density of state or not? Why not?
No.
Why not? What's wrong with my density of state? What do you think is wrong with my density of state?
Left part.
Huh? You don't like the left part? Let's see. Okay, first of all, what do you remember where was the Fermi level? Where was the Fermi level? Around 1, right? So 5, 1, let's say here. EF. So what kind of material do we know already do we have here? So here's the energy scale, right? On the bottom, the DOS scale is here, or intensity. So from this density of state, what can you tell already what kind of material that is?
Metal.
Very good. It's a metal because we do not have a band gap, right? So, and we know lithium is actually a metal, right? So that's a shack. Not shit, shack, right? Metal. Shack. Right? Good. So you don't like the empty part here. Let's see. From the k-points, we looked at one of the k-points, and I remember the lowest value I saw there was something like minus 50 eV. So you don't like my density of state. I was like, I can show you that I didn't do a mistake. So I go to my minimum energy here, and I change that to, right, the energy is in EV, so I put 50 here. Funnily, the broadening factor I use there is in Rydberg, so the units are not that consistent. So you need to be a bit careful. I rerun my DOS calculation, and then I try to open GNU plot again. Oh, interesting, right? So what do we see now? So the energy scale is different now. So last time we had from -10 to 10, and we still see there is this cutoff here that you didn't like, but now I want to highlight something. This one here, the beginning of that cutoff roughly looks like a square root, right? Did you take a course in solid state physics? What do you know, what kind of model do you know for the density of state of metals? How does it look like? Did it look something like, or the energy scale is here, right? And then we have the states increasing in density, and there's a cutoff here. Do you remember that? What does this curve look like? Yeah, this one. Does this look like a square root thing? Roughly, right? And we see the same here. The same is similar part, right? So lithium behaves roughly to some degree like the idealized metal. You will not see that for all, but here you see that because, well, the electrons in lithium are pretty simple. Good. So we remember that we have no band gap, metal. We have even the agreement with the more fundamental, the agreement between the DFT calculation and the more fundamental band model. So that part is okay, right? So what's about these states here at -45 eV? They are very sharp, right? So that is very high, very narrow. We call it sharp. Do you like that or don't you like that? The thing is, when you tell me you don't like it, I would ask you why, and when you tell me you like it, I will ask you why. So what do you think? No. Okay, do you like it?
No.
No. Okay, then tell me why don't you like the sharp levels at low energies?
Because I think I want to focus on the right part.
That is okay, so you're more interested in the valence properties.
Yes.
Okay, but do you think something is wrong with these levels at the core? Basically, the question is, do you think I did a mistake in the calculation? Did you study already the properties of electrons that are not valence electrons? So there is a very nice course here. It's called X-ray and electron energy spectroscopy, where there is one focus on core electrons, 1s electrons, and they are very helpful because the electrons here, they are very simple to describe. This one is very complicated here. The electrons mix a lot, right? The electrons here, they stay for themselves, right? And then we can describe them easily when there's a change here, right? If we remove electrons from the valence region, the electrons at the core will feel that, and they will shift a bit. And we can measure this shift with xds. X-ray photoelectron spectroscopy. And we can then quite well describe what's going on. Of course, the core electrons are very sharp, right? Suppose we shift the peak here by 1 eV, we would easily see that. If this peak would be very broad like this, and maybe there would be some other effects, and we shift there something, it would be much harder to quantify. But because the peaks are very sharp, we can get a lot of information. So the physics there is good, and the interpretation here is these are my 1s core electrons. They do not take part in the valence region, that are not part of the valence region, and do not take part in chemical bonding, at least not directly. Right. There's also Auger electron spectroscopy, XAS, and things like that. So that is a master course here, and good. Back to topic. However, mostly when we design properties of materials, we are mostly interested in the valence region. So we go back to the input, dos, and we change this back. We can, right, let's discuss, right, let's go the other direction. So what's about when I put here, let's say, 50 eV? Then I rerun the calculation. I just come in, right? Just take the photo. And then I open GNU plot. I look at the density of states again. Right. So now I shifted 50 eV in the other direction. You remember here something like the square function, the square root function, scaled up. The Fermi energy is here. Couple of peaks. And then a lot of empty space here. So what do you think? Something wrong, something good, something bad? What are your thoughts here?
You mean that peak?
Say again?
You mean that peak?
Do you think here's something missing in that region between 10 and 50 eV? No? Nothing missing? So, what do you know about the electronic structure of unoccupied states? Or let me ask differently. When you have a hydrogen atom, you know it has one electron, and it sits in the 1s orbital, right? You know so much. Can the electron go from the 1s orbital to, let's say, an orbital in the second shell? Can it do that? Are you familiar with that process? Right, we have a core and the 1s orbital, right? 1s shell, right? And then we have the second shell. We have an electron here. Can the electron go from one shell to the another shell? Yes, right? So let's say we have a third shell. Can the electron go to the third shell? Yeah. I add more and more shells. Can the electron go to the shell 999? Yes, it can. Right? It can go here. So these are so-called Rydberg states. There are transitions possible. You don't see them here because the further you go out, right, the bigger becomes your expectation value for the radius of the atom. If the radius is very big, it's very likely that it will collide with other atoms. And if it is colliding with other atoms, the electron will fall down into lower states. If you go to the outer space, there are Rydberg atoms known to have a diameter of up to in the order of centimeter, because the electron is excited into very high states. Right? Good. Now we go to the one step back. What is the largest number I can put here? In principle. Well, there is no limit. Are you familiar with quantum numbers? We had a student talk about that, right? We said n should be larger than or equal 1. Right? That was the only restriction. So we can put there a million and it still would be valid. Good. So when we go beyond the binding region, where the energy of the electron is negative compared to the vacuum level, we go to the non-binding region, but it's still possible to find states there. Our last state should be somewhere here, around maybe 11 electron volts. But there should be more, right? Because in principle, n is going to infinity, to higher and higher states, so I should have states on this whole axis. What is the reason why my density of state plot ends at 10 eV? Well, that is because I'm only asking for 60 bands to be calculated. I close this plot, I exit GNU plot, I copy my old density or my current density to a new name, and I call that total dos.old.dos. And then I go into my SCF calculation, the input for that. The calculation took a minute, right? So let's say I take here 180 bands and I submit this calculation. That will take now a bit longer. Meanwhile, you can proceed with your DOS calculation to check if you also manage to at least get the metal character of lithium, okay? And if you don't see it, increase the number of K points further, right? And increase them as long as you don't see any, until you don't see any change anymore, okay? So there's one more point I want to highlight. That is the last calculation with 60 bands took like 2 minutes. Okay? Now the calculation with 160 bands, right? 3 times the amount of bands. The initiation, right, before we start the SCF calculation, already took almost half a minute. That means we went 1/4 of the time just to prepare everything to start the calculation. This setup is computationally much more expensive. So when you do your own calculations, put as many bands as needed, not as many bands as possible, because the computational cost increased drastically. It's not like 3 times the amount of bands gives you 3 times the amount of time. You see, it's much more drastic. I'm still sitting at the first self-consistent iteration. Let's see how long that takes. Okay, now I just noticed something. So here something is very suspicious. There are almost 8 electrons missing. So the code first tries to guess some density and then computes the corresponding number of electrons. The value between the computed and the should be value should be more or less the same. So here the calculation will struggle a bit to go from the 41 to the 48. But hopefully everything turns out nicely. Okay, let's see. So the first iteration took me 230 seconds, and that is like almost 5 minutes, right? 4 minutes. 4 or 5 minutes. Good. Okay, but now it's going faster. Meanwhile, I will do something else. I will stop the recording.